Give us 1 sec and then we will get started. Can everyone see the slides? Okay. See a thumbs up.
Yeah, I can see it too. This is a disclaimer. Even though it's being recorded, we are not sending it out. If you want the information, you have to stay. We're just recording it for our own purposes.
Okay, let's go ahead and get started. So welcome everyone to Unit 1 Concept Review. We'll be covering pretty much all of the material through last week when the snowstorm happened. And then we're hosting a review session on Wednesday evening that will cover material from those videos that you guys were supposed to watch, as well as the material that's going to be covered tomorrow or Monday and a little bit on Wednesday before the exam. So getting started, here's a list of the topics that we came up with for Unit 1. This definitely looks like a lot, but we're gonna try and break it down piece by piece and hopefully make it seem not so much for you guys. So getting started with gas laws, we first looked at Boyle's law, which simply states that the volume and pressure of a gas are inversely proportional for fixed temperature in moles. And we can write that as an equation V equals K as a function of N and T divided by P. So this relationship captures Boyle's law in words. And then K in this case depends on our temperature and number of moles. And we can see that by looking at our graph here. So this black curve is just our initial moles and temperature. But then if we increase our initial amount of moles or increase our temperature, we'll see that 1 over pressure decreases. So our slope decreases. Or vice versa, if we decrease our amount of moles or decrease our temperature, 1 over pressure will increase. So we get a steeper slope. And then moving on to Charles' law, this is just volume and temperature are directly proportional for constant pressure in moles. Again, mathematically, we can write this as V equals K P N T, where K is a function of P and T. And in this case, K depends on pressure in moles. And again, we can look at these graphs and say, here, this black line is our initial pressure in moles. And then if we either increase our pressure or decrease our number of moles, our volume is going to decrease. So we get a shallower slope on our graph. Or if we decrease our pressure or increase our number of moles, we're going to see a steeper slope on our volume versus temperature graph. And one thing to pay attention to here is that temperature is in Kelvin, not degrees Celsius, because remember, Kelvin is our absolute temperature scale. So we go through the origin on this graph. If we were given this graph in degrees Celsius, we would see our x-intercept at -273 instead of 0. Just something to keep in mind, especially with units and converting between Kelvin and degrees Celsius. And then finally, we didn't talk about these two laws as much, but Avogadro's and Amonton's laws are both part of these gas laws that we looked at. Avogadro's law, this is hopefully a refresher from first semester. Volume and number of moles are directly proportional for constant temperature and pressure. And we write that as V equals K function of PTN, where K depends on pressure and temperature. And if we were to graph our moles versus volume graph, we would see a linear relationship. And then similarly with Amonton's law, pressure and temperature of a gas are directly proportional. And we can write that mathematically as P equals K as a function of NV times T. And then similarly, our graph is a linear curve between temperature in degrees Kelvin and pressure. Again, note temperature is in Kelvin, not degrees Celsius here, because we have to go through our origin. So then we took all of these laws and used them to derive the ideal gas law. So I'm going to walk through that with you guys right now because some of the like math behind it isn't like super clear. So basically what we're going to do is apply other gas laws to a gas law that we're starting with. So let's say we start with Boyle's law, which is PV times K N T. So right now I have pressure and volume are inversely proportional to each other. And somehow I need to figure out how moles and temperature are related to these in order to get my ideal gas law. So what we can do is say PV is equal to, I'm going to call this K1. And let's say we're fixing our pressure now. And we're going to look at moles. So we know from Avogadro's law that volume and number of moles are directly proportional. So in this mathematical expression, we're going to keep temperature inside our K constant, and then we're going to write N on the outside, because now we see using Avogadro's law, if we increase the number of moles, we'll increase our volume. And then we can do the exact same thing with temperature now. So let's say we're keeping pressure constant again, and now we're going to keep moles constant. If we look at the relationship between volume and temperature, we know from Charles' law that these are directly proportional. So I'm going to call this K2 now. N is still outside of our parentheses of our K function. And now we write temperature directly proportional. So if we look at this again, these are all constant. If we increase our temperature, we know that we're going to increase our volume. And now this hopefully looks familiar. We can just rewrite this as PV equals N RT, and that's our ideal gas law. Let's see, I'll leave this up there. Oh, okay, never mind. And here's our ideal gas law. Hopefully you guys have this memorized by now. And then from the ideal gas law, we derived a law called Dalton's law of partial pressures, which says that the total pressure of a mixture of gases is equal to the sum of the individual pressures of each gas. So really mathematically, all this is the total pressure is equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3 for however many gases we have. Or we can rearrange that expression using the ideal gas law, and we can say that the total pressure is equal to the sum of all of the moles of our gases, so N1 plus N2 plus N3 times RT over V, and that will get us the same expression. And then this bottom equation can be further manipulated to get what's called the mole fraction. So that's just basically the ratio of moles to total moles over the, or equal to the ratio of pressure of whatever gas sample you're looking at to the total pressure. And then we also talked about deviations from the ideal gas law. So remember that at relatively low pressures or gas densities or particle densities, we see that most molecules follow the ideal gas law. But as we start increasing the pressure or the particle density, we get these negative deviations in this curve here. And that's due to our attractive intermolecular forces. Whereas if we increase our pressure even more, so starting around like 75 atmospheres, we'll see that now our molecules are starting to deviate positively from the ideal gas law. So the pressure is even greater than what's predicted by the ideal gas law. And that's due to the repulsive intermolecular forces, because we're packing those molecules so closely together that the electrons in those molecules are actually starting to like overlap and repel each other. And that's what's causing these repulsions. And then something to be really careful about, like on the exam, if we ask you guys about deviations from the ideal gas law, is that pressure is not decreasing here. We're still seeing an increase in pressure as we're moving along this axis, but it's less than what's predicted by the ideal gas law. So that's a really like subtle distinction that you guys should be aware of. And then similarly for our positive deviations, the pressure is still increasing, but it's increasing a lot more than what the ideal gas law predicts. Then transitioning, so the ideal gas law and all of those gas laws that we previously talked about dealt with macroscopic properties, things like pressure, temperature, volume, whereas our kinetic molecular theory is our microscopic explanations for those observations that we see macroscopically. So these are the 4 postulates of KMT. Make sure you guys know these inside and out and are able to apply them. A lot of them are pretty self-explanatory. The one that's really important and you will almost always come back to is that pressure is the force of particle collisions on the container. And that's determined by 2 factors: the force of collisions, or how hard these particles are hitting the wall, and the frequency of collisions, or how often the particles are hitting the wall. So anytime you guys see on the test using kinetic molecular theory, chances are we're looking for something about the force of collisions and the frequency of collisions. So if you can tie those 2 things back to whatever the question may be asking, you'll probably be in really good shape. Then we talked about temperature involved in the kinetic molecular theory. And we said that temperature is actually a measure of kinetic energy and can determine the speed at which molecules move, which is called our root mean squared speed. Here are 2 of our equations. So this is the average kinetic energy, which is also equal to 1/2 mv squared. And then we see that our VRMS is equal to this equation. One thing to note when using this equation is that molar mass is in kilograms per mole, not grams per mole. Be sure you convert properly, otherwise you will get the wrong answer. And then in addition to these 2 equations and properties, we also can like model this in terms of what's called a Maxwell-Boltzmann distribution, which is kind of this graph here where we have speed on our x-axis and number of molecules on our y-axis. And we see that each of these molecules are going at different average speeds, where the total area under our curve is the number of molecules we have. And then usually the top of our peak is going to be our VRMS. So A will be going the slowest because more molecules are at a lower VRMS. B will be going in the middle because it's in the middle. And C will have more molecules at a faster VRMS or a higher temperature. And we can figure that out based off of our VRMS equation. Then we also talked about mean free path and collision frequency. So the mean free path is simply the distance molecules travel before experiencing a collision. And it depends on the size of our molecule and the particle density. So if we have larger molecules, they're going to collide more often. So we're going to have a smaller mean free path. And similarly, if we have a higher density, that means that there are more molecules in our container, which means that they're going to collide more often. And similarly, they're going to have a smaller mean free path. Then collision frequency is pretty much exactly what it sounds like, how frequently or how often the molecules are colliding with each other. And that really depends on the mean free path and the VRMS. If you guys ever get confused about units for any of these, just think about frequency as like number of collisions per second. And if we look at this equation, we see VRMS over lambda. VRMS is in units of meters per second, and mean free path is in units of meters per collision. So when we take this equation, our units should be rearranged that we get seconds per collision. And then collision frequency depends on mean free path and VRMS, like I said, in this equation, but we can also describe it qualitatively. So faster moving molecules will collide more frequently just because they're moving faster. And then a smaller mean free path means that there are more collisions per unit time because they're traveling less distance before colliding compared to molecules that would be having to travel a larger distance per unit time. And then finally, the last part of KMT that we really talked about was effusion versus diffusion. Effusion is the rate at which gas escapes through a hole, and that depends on the speed and the mass of the molecule. Really, it's just the mass. So faster molecules will effuse faster, pretty self-explanatory. But then lighter molecules will move faster and therefore also effuse faster. And we can write this mathematically as what's called Graham's law, where we're comparing the rates of effusion for two gases, and it's just the square root of the ratio of their molar masses. Again, notice here that molar mass is in kilograms per mole, not grams per mole. Something to look out for if you guys are ever asked to calculate a rate of effusion on the exam. And then finally, for diffusion, it's simply the spontaneous mixing of gases at constant pressure. And this depends on the collisions, which are determined by the size of our molecules and the particle density. So if we have larger molecules, they're going to collide more often and therefore diffuse slower because they're colliding more often. And similarly, more molecules in our container will collide more often. And as a result, they'll diffuse slower because they're running into each other more. They can't freely travel. Now I will let Mark take over.
Yeah, you want, yeah, okay, cool. Okay, can you hear me? Jack, someone? Okay, cool. So I'm going to start with reactions pretty much. So we can model reactions in these energy profiles to show how the energy changes over the course of the reaction. And if you have to know this graph pretty well. It's very important to understand everything that's going on. So you can see the y-axis represents energy and the x-axis represents progress of a reaction. So as the reaction goes on, the energy has to increase in order to hit the transition state. And this is because if the transition state was lower than the reactants, then the products would already be formed. That's not a reaction. The transition state will always be greater in energy than the reactants. However, the products can be higher or lower than the reactants. In this case, we see that the products are higher, which means that the net change in energy was positive, meaning the products have more energy than the reactants. So that's an endothermic reaction. Versus if the products were to be, say, down here, we would see that the products lost energy relative to the reactants, meaning that energy had to go somewhere, so it was released, making it an exothermic reaction. So that's an important distinction between the two different types of reaction. And the fact that it's endothermic or exothermic doesn't tell you anything about the speed pretty much of the reaction, or really it doesn't tell you as much as you think it would. It's really just determining the change of the energy in the products relative to the reactants, and that's really what it's important for. And an important note is at the top, like I said, this is transition state, and you just got into multi-step reactions, I believe, which also has intermediates. However, that will be covered in the review whenever the next review is. I'm not sure they determined that yet. But right now, I'm just going to talk about this simple energy profile, or reaction energy profile. Reactants need the energy to cross the activation threshold and react to form the product. So in order for this to get over the hump, the reactants must have the threshold energy in order to react. And if you remember that shifty change of the Maxwell-Boltzmann distribution being lined up against a reaction energy profile, it really helps understand the process. So If you don't remember that, I would go back and watch it. I do not have the same graphic design skills as they do, so I did not recreate it here. And as we have these reactions, we have different reaction rates. So the rate is described as either the change in concentration of the products or the change in concentration of the reactants. So I've written here, we can describe the rate of a reaction with the rate at which the product is being formed or the rate at which the reactant is diminishing, because we want to know how fast basically the products are being formed. So if the reactants are diminishing, that means they have to be going to form the products. So that's why we put the negative in front of it too, because the concentration of reactants will be changing in a negative sense, but the rate must be positive. So we add the negative in front of it in order to flip it back to a positive rate, right? Because over time, N2O5 is going to decrease in concentration. So the D, this is not a good color. So the DN2O5 is going to be a negative number, because each time we take note of that concentration, it's getting lower and lower as the reaction proceeds forward. And since that's going to be a negative number, we want to add another negative in front of it to switch it back to a positive number, because the rate is, we're describing how fast the products are being formed. And like I said, that can be done in terms of the reactant or the product. So if we're talking about the change in concentration of the products, DNO2 is going to be a positive number because the products are gaining in concentration. So we don't need to add a negative sign in front to flip it. That's the easy way to basically look at the difference between the rates of reaction when we're talking about products and reactants, which is also seen down here in this chart. And this is a really nice chart because it also has the stoichiometric coefficients and how they factor in. Remember, if it's kind of hard to tell by these charts, but since we want to get these in common units, if A were to have like a 2 in front of it, that means that it's being diminished at twice the rate of C would be created if C was equal to 1. So in order to get that back into familiar units with that C value, we're gonna have to divide it by 2, which is why it's 1 over A or minus 1 over A, because we're talking about the reactants. So that's an important note. This is a very helpful equation if you understand it. So I would do your best to know it. Okay, rates and rate laws. So rates are different than rate laws. The rate law relates the rate of the reaction to the concentration of the reactant. This is not always equal to stoichiometric coefficients. That's an important note because a lot of people get that messed up. A rate describes how fast a reaction goes based on the concentration change of either reactants or products. However, a rate law relates the rate to the concentration of the starting reagents. An important note is that rates are different and rate laws are different at different temperatures, because a temperature will adjust the Maxwell-Boltzmann distribution, which will change the number of will change how fast the reaction proceeds. So if you look at the top here, we have displayed a rate law versus what we just talked about was a rate. If you notice at the rate, we were describing it as a changing concentration of the product or reactant, versus the rate law, we're talking about the initial concentration of the reactants. And I have another slide here that I like better that, I guess that was it actually. So this was the slide comparing a rate and a rate law. So yeah, that's the main difference. Hopefully that makes sense. That's a really important distinction. A lot of people mix that up. The main idea that you need to know is, first off, they're very different, but if you, easy way to know the difference is if we're talking about a rate law, you have to have rate equals something, versus a rate is not that is not the case. So remember, rate equals something for a rate law. So that's what we're talking about, the concentration of the reagents, versus a rate, we're talking about the change in concentration by the reagents or the products. Okay, Method of initial rates. So this is how we determine the reaction order. So this takes a lot of practice, basically, and so I put an example up here because it's kind of hard to explain without an example. So we basically want to divide one trial by another. So if we see the difference between these two trials, we can tell that it's a difference in concentration of B, of the concentration of B. So we want to divide the rate laws of each of those trials by each other in order to get the reaction order. So you can see right here, it gives us basically the first step. So we know the initial rate for trial 1 is 0.4 equals 0.2 to the x and 0.2 to the y times k. Sorry, I ran out of room there. Trial 2, it's 1.6 equals a concentration of 0.2, which is A, and then the concentration of B, 0.4. I didn't hear, don't forget to add your zeros here, makes sig figs easier. And then to the Y, and there's also a K. So when we are doing this method, we want to divide one rate law by the other. So it's easier to put the larger one on top. That way we're dealing with whole numbers instead of fractions. So, or not whole numbers, I guess just numbers greater than 1. So 1.6 divided by 0.4 equals 0.20 over x, and 0.20 over x, 0.40 y, and then 0.20 y. So then we divide 1.6 by 0.04, we get 4 equals, and if we look at this part of it, 0.20 over 0 to the x over 0.20 to the x, we can basically say 0.20 over 0.20 and put that all to the x, and this would be 1 to the x. So it doesn't matter what x is because that's going to stay 1. So we can write this as 1. And then the second half of it, we can write as 0.4 over 0.2 to, sorry, this should be a y, to the y. And I'm gonna move this over here because I'm out of space. So that would be 4 equals 2 to the y. So that means y equals 2. So the order for reagent B would be second. However, we also need to find the order for reagent A, which would end up being first. I'm not going to walk through that again because it's the same method that I just went through. And so that's just a quick example. If you're given data sets with more than just 2 experiments, use the easiest combination to save time. So remember, this exam is probably going to be a bit of a time crunch, so do the best you can to save time. That involves memorizing all the formulas you can. I believe you're allowed to use your book, but you really want to memorize them because it's going to save you a lot of time and you really need your time. And that involves all of the equations or formulas that Jack went over, kinetic energy, root mean square speed, mean free path, frequency of collision, etc. There's really a lot. If you know the formulas for this exam, you're off to a good start, but obviously you have to understand what the formulas mean, the connections formed by the formulas, especially in the ideal gas law. You saw how much that was true. Okay. So the integrated rate law. So it's pretty much what it sounds like. There's not much to it. It gives us a way of determining how much reactant is left after a given point in time. You can use this to determine the half-life formula, but again, you want to memorize the formula so you can save time. So I would just memorize the half-life formula. And along with the integrated rate laws go these graphs. So we're obsessed basically with straight lines. And with each of these different order reactions, we can see that if we take the concentration of A and manipulate it in one way or another, we will get a straight line, such as ln A here, or 1 over A here. And then in 0th order reaction, it's simply A. Now, this is actually really important, even though you might think it's a minor detail, because some questions will work that in one way or another. I had a question in my office hours, I know, that went like that. I'm sure you'll see an example through your studying that has this in some way or another, or they might just straight up give you an assess the accuracy with these graphs and ask you, are they wrong, right, etc. So it's important to know these relationships. Yeah, so that's integrated rate law. Integrated rate laws are very useful for kind of like the solving like number questions. Like they'll give you initial concentration, a final concentration. You can solve for K if you know the time between those two concentrations, and then you can use that to find the rate at a specific point in time. There's really a lot you can do with the integrated rate law. An important note here. Okay, I'll get to it when I get to that. So these are more graphs. So like I said, it's really important to know the graphs. There's a lot of different ways we can present them, but they're really important to understand, such as the top, the change in concentration of the reactant with time. And then it's displayed as basically the rate, it looks like, with time. And then we see the ways that we can make K linear. So like I said, it's important to know these for a question like and assess the accuracy if they give you different graphs, or if they just give you graphs and to say like what order reaction is being represented. I don't think you can draw anything because the test is online. I might be wrong, but I'm pretty sure that's not the case. But regardless, you still need to know these graphs. Okay, so these are all the formulas that are associated with the rate laws. It's really important that you know these well as with the other ones, because there's really not a lot of ways you can go wrong with some of these questions. A lot of them are just plugging in numbers and solving. So if you plug in the wrong number, or if you plug into the wrong formula, if you so much as like miss a minus sign in the formula, you can lose a lot of points. I want to say in my exam last year, I think I was using the Arrhenius equation and I missed like a minus sign and I got like a 2 out of 10. I was kind of upset about that. Just a side note. So a reminder to always make sure that you double check the formulas you are using are correct, because there's not many ways you can go wrong with them besides for just plugging it in incorrectly. So it will cost you big if you do not do that. More specifically for this chart, K units, these are also important. Sometimes they'll give you the K units and they won't tell you the reaction order. They'll expect you to know based on the K units, since the K units are different for each reaction order. The same can go with the linear plot. As I said, the half-life is really important. I know you had a question like that in your homework. These are all just really important formulas. This whole unit is just grounded in these formulas, but it's important you understand the relationships that these formulas represent. For example, if you look at half-life of a first order reaction, you can tell that the half-life of a first order reaction actually does not change over time, because it doesn't depend on the initial concentration of A. Instead, the half-life is going to be the same over the entire course of the reaction. So if you have a question that's dealing with a reaction that has a constant half-life, If you notice that in different data sets that they give you, you know that you're dealing with a first order reaction. So versus if you see a reaction where the half-life is increasing, right? Yeah, that would be increasing as the reaction proceeds. That means that you're dealing with a second order reaction because A will be decreasing, meaning the entire half-life will be increasing. And the opposite goes for a first order reaction, or I'm sorry, a zeroth order reaction. In a zeroth order reaction, the concentration of A will decrease with time, which means the half-life is actually going to be decreasing as the reaction proceeds. So you can see that there's a lot of really interesting relationships you can see through these graphs and through these formulas. So it's important that you look through them and understand them. I believe this is the last slide. So I just wanted to go back. Oh, yeah, this is kind of what I mentioned at the beginning, the connection between the Maxwell-Boltzmann distribution and the reaction energy profile. So going back to last week, sorry to people who came to my office hours, by the way, these are pretty much the same slides I used in my office hours. So this was probably not last week, maybe 2 weeks ago. Know the effects of temperature in a graphical and conceptual way. Then we can get into formulas that will help us out. However, you will have to understand and be able to explain it. So I'm sure you figured out by now if you've taken Chem 121. If you did not take Chem 121, it's important to note that you will not get by basically with like surface level explanations. You have to be specific and thorough and accurate. Like some people try to be broad and accurate, like not knowing, if you don't know the specifics. And I mean, I was responsible for this at a lot of points in different classes, that you can just speak broadly and say stuff that you know are factual instead of being specific, because you don't know the specifics as well. That will not get by in this class because we are looking for the specifics. So make sure you understand the specifics of all of these concepts, and make sure you are as specific as possible in your responses given your time restrictions. So you really have to know these well if you want to do well, because you're going to be probably, I heard last semester's exams were always pretty much a time rush. So you're going to have to get through a lot of material. So you're going to have to know the material really well and be able to be very specific with it in order to get full credit. So I think Jack touched mainly on this, but I'll go over it quickly, how the Maxwell-Boltzmann distribution changes with the increase in temperature. This means that if we have an activation energy that say was like right here, then after we raise the temperature, there's a greater number of molecules that, or atoms that have the energy needed in order to react, which would be basically the integral of the formula or of the line. So you can see by the shaded area, there's more in, or at least there should be more. I don't know if I drew it so that there would be more that can react if we raise the temperature. And it's even more so true if we have a higher activation energy, although I think that was in your material from this week. So they'll go over that at the next review session. Yeah, so like I said, I don't have the design skills to really rotate the Maxwell-Boltzmann distribution, but that was a really, I know it helps a lot of people understand this concept. So I would go back to that lecture and watch it if this does not make any sense or if you have not seen it before. So I think that, oh, no, there's more. The higher, oh yeah, so this is what I just said. The higher the activation energy, the greater the effect from a raised temperature. A lower fraction of the molecules already have the activation energy, so a higher temperature has a greater effect. And how does the temperature affect the rate law? So remember, rate law is rate equals K times concentration of A to the X times concentration of B to the Y as an example. And it doesn't affect the concentration of A or B, so it has to be K. So when we raise the temperature, we're affecting K. And oh, I mentioned the Arrhenius equation here, although I'm pretty confident that was this week's material as well. So you can ignore that and they'll go over it at the next review session. Okay, cool. So that's all of the material we have. I don't know, Jack, did I miss anything?
No, I think that covers it. So if you guys have questions, feel free to either raise your hand and we'll call on you guys, or you can try and put them in the chat.
I don't see names here, so I'm just going to click the ask to unmute. Hopefully you see something pop up on your screen.
All right. Is it all right if I ask a question?
Yeah, that's fine. Or you could just unmute yourself and ask.
Okay. So could you explain the difference between rate and rate laws again? I wasn't sure that I caught the concept.
Yeah. So yeah, this was my slide on the difference. So if we go back to chat, can you handle the chat? It looks like there's a question. Maybe that was it. Yeah. So sorry. So what you see up here is an example of a rate law. It's expressing the rate of the reaction in regards to the concentration of the reactant. Versus if we're talking about a rate, we're looking at the rate of the products being formed relative to the change in the concentration of the reactants or of the products. However, for a rate law, that's not the case because it's being expressed as the initial concentration of the reactant. Jack, do you have anything to add?
No, I'm trying to keep up with questions in the chat, so sorry if it takes me a minute to respond to you guys.
No, it's good. We can go over the chats aloud too. That would probably save time. So first off, does that make sense to whoever asked that question?
Yeah. So initial one is the rate law, right? And then the rate is not. It's the change over time. Okay, I got it.
Yeah.
All right, thank you.
Yeah. Jack, do you want to elaborate at all? Because I know it's a really important note.
Do what?
Elaborate at all on the difference between a rate and a rate law?
I think you covered it well. Anytime you see rate law, always think rate equals something. Like, don't just put Ka or Ka squared. It's always rate equals and then whatever it is.
Yeah, there's also that conceptual difference in that a rate law is talking about a concentration, the rate at a specific concentration, whereas the rate's giving you the rate of the reaction as a change in concentration. Okay, I'm gonna look at these questions. Would you be able to go back to the slide with the central plots? Yeah. Yeah, these ones hopefully, if not, chat me again. I would just take a picture of it. Could you explain more about the relationship between the mole fraction and Dalton's law? Jack, this is your material. You want to go over it?
Yeah, can you go back to that slide?
Yeah.
Okay, so basically for Dalton's law and the mole fraction, we're just looking at this bottom equation. So we can say, let me see if I can annotate on your screen, Mark.
You should be
Okay.
able to.
Yeah, so we can say P total, just gonna write PT, is equal to P1 plus P2. And then we know that from the ideal gas law, that that's equal to N1 plus N2 RT over V. This should be in parentheses. So then we can basically break this up and say that P1 plus P2 is equal to N1 RT over V plus N2 RT over V. And then since these things are volume, temperature, and the ideal gas constant would be equal between both of these, we're essentially going to ignore them for right now. And then we're going to write P1 plus P2 is now proportional to N1 plus N2. And then you can say, if you want to like take the difference of these, you can say P1 over P2, that ratio is equal to N1 over N2. So this is kind of getting at our mole fraction. Or really, if you want like the actual fraction, P2 and N2 here could be the total number of moles and the total pressure. So P1 N1 over P total N total. Does that help clear it up? It's basically
important
just,
note.
or yeah, go ahead, Mark.
Yeah, sorry. I was going to say important note is to understand why this makes sense conceptually too. Like I said, you need to know more than just the formulas. If we have more moles, we're going to have more collisions. Remember, pressure is force per unit area of the container walls. So if we have more moles in a set volume, that means those moles are closer to the container walls. They have to be more scrunched together. So that means there's more that's going to be closer to the walls. So they're going to hit the walls more often. So the force is going to be greater. And that's why the pressure will increase when we have more moles. Actually, I don't think that's what you're talking about. Oh, no, it kind of was. You're relating pressure to the number of moles. But yeah, that's an important conceptual connection to make. Sorry, go ahead with whatever you're saying. Hello?
What?
Were you saying something else?
No, I'm
okay.
trying to respond to the chat. If you guys can put the chat for everyone to see, that way we can, Mark and I can both see it. We'll just go through the questions out loud that way. I feel like that's easier than us trying to type.
Yeah, and if you don't have any questions, remember you're always free to go. You're never held to be here. Thanks for coming. But if you want to see the answers, we'll go through them. So the next one I see is this test going to be more math or conceptual? I feel like we had more formulas in last semester. For sure, there's going to be a lot more math, but that does not mean you're not going to see any concepts. You're going to have to explain the concepts behind the math. Some of them will be straight conceptual, some will be straight math. But we still go over chemistry in a conceptual way, so you definitely need to know the concepts. But memorizing the formulas is a good start and is definitely necessary to do well. And it doesn't stop in this unit. I believe the next 2 units or 3 units all have more math than we had last semester. But we'll still see a lot of concepts. Next, do we need to know the specifics of catalysts and their effects on reaction rate? If so, can you explain? This is in the material that will be covered at the next review session, but I don't think we even got the catalysts yet in the lecture.
No, we're talking about catalysts on Monday, I believe. So stay tuned for that.
Yeah. Remember, it's just whatever we go over in lecture and whatever is in the book, it's fair game. So we'll see what they go over. Honestly, I'm not sure how far we're going to get. Sorry, I can give a more specific answer.
Yeah.
Jack, you want to go over this next one?
Yeah, I see. Why is the mean free path not affected by speed, but collision frequency is? So mean free path really is just looking at one molecule moving through space. We're not really concerned about its speed so much as its distance. So a faster moving molecule won't necessarily like collide with another molecule faster, I guess, if that makes sense. It's just that a larger molecule will travel a smaller distance before colliding. Because if you think about mean free path and speed, mean free path is almost that distance per time. So if you have a faster moving molecule, it might cover more distance per unit time, which means that it has a greater mean free path, but it's also like higher speed. But you could also have a smaller molecule that moves just as far, but is going a different speed or something. And then collision frequency does depend on mean free path because that's like how far the molecules actually like, or I guess now I'm describing mean free path. Collision frequency is how often they collide. So if they're moving faster in their container, they're still like covering more ground. So they have a higher mean free path, but they're also colliding more often because they're moving faster. Hopefully that makes sense. Mark, do you have anything to add?
No, why is the mean free path not affected by speed? I'm sure you got it. You can see the connection in the formula as well. Like I said, just make sure you know the conceptual understanding, which Jack went over. Next I see is if KE average equals 3 over 2 nRT, what does KE total equal?
I think that was a typo in the equation. KE average should be 3/2 RT, and KE total I think is 3/2 nRT.
Ooh.
Someone said that's what they had in their notes.
I thought KE average would be 3 RT over Avogadro's number, and KE total would be 3/2 nRT. But I don't know.
KE total 3/2 nRT. One of them is 3/2 nRT. One of them's 3/2 RT. I think there's just the difference is the n. Jack said the formula is wrong.
On the slide, it has KE average as 3/2 nRT. And I think that's for KE average, not KE total.
Yeah, that's right. So KE total is 3/2 nRT. When we multiply by the number of moles, that's how we get the total. So when we're taking the average, we're basically doing the average or the total divided by the number of moles, which is why KE average is 3/2 RT. Right?
Yeah.
Jack, that's right.
Mm-hmm.
Yeah, sorry about that. Hopefully there's a way we can send out a correction about that to the people who already left. Okay, why does half-life increase with time for a second order reaction but decrease with time for a first order reaction? I'm not sure if that's in the scope of this class. Jack, do you know?
So let's see. Half-life increase with time. So half-life doesn't decrease with time for a first order reaction. Half-life is constant for a first order reaction. And
I think they probably mean 0th order.
Okay, in that case, yeah, I don't know. I think that's probably outside the scope of this class. If I had to guess, it would involve something about K changing, but like you probably won't be asked that on the exam. Let's see, I see one. What exactly are the variables that affect mean free path? We mentioned size and particle density, but also saw the letter D and Na in the equation. What do these variables mean? So can you go back to the formula, Mark?
Yeah.
So D is the diameter of the molecule, so that's the size. Na is Avogadro's number. And then we say particle density, but that's in our equation represented by pressure, because we know from the ideal gas law that pressure and particle density are directly related. Hopefully that clears that up.
Okay, next I have a private one. Can we go over rate expression versus rate law once more? Okay, Jack, do you want to do it this time? I don't think I'm coming across well.
Yeah, I can try. So rate is basically a change in concentration over time. And we can describe it as the disappearance of a reactant or the appearance of a product over time. A rate law relates how the rate, so that disappearance of reactant or appearance of product, changes with the concentration of our starting material. So really the main takeaway is that a rate it is a mathematical expression, but it's not an equation. It's just a description of how our concentration is changing with time. But a rate law is relating the rate, so our concentration changing over time, with the concentrations of our starting materials. So if you're ever asked to write a rate law for something, you should always write the equation rate equals, and then whatever the actual like rate is equal to in terms of the concentrations of our starting materials. Hopefully that helps. Feel free to unmute if it does not make sense still.
See another one, why does half-life increase with time for a second order, but decrease with time for a first order? Remember, I think you mean 0th order and second order. Like we said, we're pretty sure that's outside the scope of this class. You can ask the instructors Monday, but I'm like 99% sure it's outside the scope. It's just a way for you to tell the difference if they give you data. Could you go back to the activation energy and its graph? This. I'm not sure if this is what you're talking about.
Yeah, I meant if you could re-explain it again, please.
Oh, go over it again. Okay, so they'll talk about this, I think, more at the next review. But basically, I'm saying if you have an activation energy that say is right here, when we raise the temperature, we're flattening the Maxwell-Boltzmann distribution, and we have more molecules that have the energy needed to react. So, and that would be represented by the integrals, so the areas under these curves. So the blue is supposed to be greater than the green in this example. I'm not sure if it's actually that way, but that's what happens when we raise the temperature. And if we have an even higher activation energy, so let me do it as EA2, this is EA1, then the increase in temperature is even more meaningful, meaning it gives unproportionately more molecules the sufficient energy to react than the lower activation energy. And that is representative in somewhat in this reaction energy profile. So the molecules have to have enough energy to get over this